about the gravitational waves, first I will give a little bit of an introduction about the astrophysics part and what are the things we started before we come into the gravitational waves. So this session, mainly I will focus on two parts, like the previous sections, like with the things we know about the astrophysics and the things we considering when we're dealing with the astrophysics, like generally what we are doing. And then in the second part that I will going to move into the gravitational waves, where we're going to discuss like we're going to have a idea about what is the gravitational wave, how it is going to happen currently, what type of institute and like how they're going to detect these information, and with these information what kind of a resource that we're going to get, we're going to discuss in here, right? So as I said, like in the start of the topic, what is astrophysics? Like, so the physics, like physics is a broad area, like you may also know that physics is the in my point of view, like it is for the everything, right? And uh, also like for the physics, like when we having a very incident, like we going to need something to explain that one, so we are using those concepts with the mathematics as a language. Then with the different scenarios, like we have the chemistry, like the other parts also deriving from the physics. It is my opinion, but I hope like everybody is going to agree with that one. Then the astrophysics is a one area where the physics also related with. Normally the thing is like in our earth where we living, like we define the physics, but outside of the planet we are living, also there is another object. So when we talk about these things, like the things which is outside of our earth, we are saying as the astronomy. So in the astronomy, the things when we dealing with the physics, we are saying that is the astrophysics part. Now in the astrophysics, we are not only discussing about the position or the motions in the space about the object, but the nature, how they do in that one, what kind of things involving with that one, how long they formed and how far they're going to stay there. Likewise, the vast number of information we are collecting that one, right? So when we come into here, like as I said, like we astrophysics dealing with the things outside of our planet, right? When we're coming out, like normally we are saying the things about us as the sky. So in the sky there is so many things we're going to have: our solar system, stars, comets, galaxies, like many types of objects, asteroids, like there is many types of things is available, right? So when we going to deal with these objects, like in the physics manner, like then we're going to have the concept called the astrophysics. Now when coming here, like as an introduction, like for the gravitational part, like we need something like, okay, where are we going to relate the gravity? So let's start with the planets. Like we know that in the A levels, or like when you're learning, like we also know that the planets, they have in their own gravity. Then the sun is giving gravity to the planets. Then the galaxy, they have in their own uh, gravity. The comets, they also sometimes they having the gravity effect, so that's why they also sometimes move in orbital planets, right? So that kind of thing is happening, right? So first let's see about the type of planets. So there is a type of classification of the planets uh, uh, with their properties. So if you have a gas planets like the Jupiter, Saturn, Uranus, Neptune, like we are saying, those are the Jovian planets. Then if you have the rocky planets, that means like very solid surfaces are there. Like most of the planet is covered with the rocky. Then like the Mercury, Venus, Earth, Mars, like we are saying those are the terrestrial planets. Then there is another type of planets like which is similar in the shape of the our moon, right? So we are saying those planets as a celestial, sorry, protoplanets. Then the planets out of our solar system, we are saying as the exoplanets. But when you come into the exoplanets also, there's a many type of classifications will be there. So I had some small clip in here. So let's see, and let's get an idea about that one. Wait a minute, I will share the sound with this one.
Probably familiar with the major types of planets in
I hope you can hear the sound, the video.
We can hear.
Okay.
our solar system. You know, there are some smaller, rocky planets and some giant gas planets. The rocky, or terrestrial ones, are closer to our star, the Sun, where it's much warmer, while the giant gas planets are farther out in the cold. But what about other planet systems we're finding out there among the stars? For the most part, they don't look a whole lot like ours. Turns out, there doesn't seem to be a typical arrangement for planetary systems. Yep, all planetary systems might be weird. Most other systems of planets are certainly arranged differently. Sure, there are lots of planets out there the size of Jupiter and Neptune and Earth, but their Jupiters and Neptunes can be way closer to their stars than ours. Some as close or closer than the orbit of Mercury. So scientists who study these exoplanets, planets outside our solar system,
Excuse me,
find
sir.
themselves using terms like hot Jupiters and
We can't see the video.
Oh, you can't see the video. Oh, okay. Can you see the screen of a video now?
Now we can see
Okay,
a
sorry.
video.
Right.
probably familiar
Okay, I'll
with the
start from
major
the
types of You're probably familiar with the major types of planets in our solar system. You know, there are some smaller, rocky planets and some giant gas planets. The rocky, or terrestrial ones, are closer to our star, the Sun, where it's much warmer, while the giant gas planets are farther out in the cold. But what about other planet systems we're finding out there among the stars? For the most part, they don't look a whole lot like ours. Turns out, there doesn't seem to be a typical arrangement for planetary systems. Yep, all planetary systems might be weird. Most other systems of planets are certainly arranged differently. Sure, there are lots of planets out there the size of Jupiter and Neptune and Earth, but their Jupiters and Neptunes can be way closer to their stars than ours. Some as close or closer than the orbit of Mercury. So scientists who study these exoplanets, planets outside our solar system, find themselves using terms like hot Jupiters and warm Neptunes. Plus, there's a whole range of exoplanet sizes, from much smaller than Earth to even bigger than Jupiter. To help describe what weight class each of these planets belongs to, we often refer back to the different planet types in our solar system, using terms like mini-Neptunes and super-Earths, or super-terrestrials. We're constantly learning more about exoplanets, and our ideas about them are changing as we go. Ideas about how these different planet types relate to each other, and what their variety can teach us about our own weird little solar system.
Okay, I will come back to the presentation.
You've seen weird, wonderful worlds in science fiction. We don't yet know what sorts of life might exist out there, but some of the planets, not unlike the ones in your favorite stories, are real.
So you can see the screen again, the presentation slides.
We can see the presentation slides. Sir.
So I think now you're having a little bit idea about the planets. Like, we are not going in depth with that one. Right now, let's move to another one, stars. Because the star is the important thing in our solar system. We know that one. Without the star, we also not going to exist. Like we also saying the star is giving the life. Like, so when coming to the, like, in the physics part, like, there is some areas where the stars going to born. So we are saying those areas as a stellar nurseries. Nurseries, it's like that term is very familiar to us. Like, yeah, we go into the nursery, like this, the children with age 2 to 5, like they go into the nursery or preschool. Like sometimes we are saying the preschools, nurseries, like we are telling. So now the question coming, like the stars also in such a places. No, in here the nurseries have a different term. Now the, like, when we growing something like a plant also, like we are saying the plant nurseries are there. So likewise, the stellar nurseries, where are the areas, like where they provide in the things to born the star, we can see. So normally in the nebulas, like we are getting such a things, right? Then in the nebulas mean actually the plasma. Like plasma mean you learn about like the solid, then the liquid, then the gas. Then the plasma is the fourth state of the matter, where when we are getting the energy through the temperature, the gas is going to ionize and they separate into two different parts, the positive ions and the negative ions. So they try to stay there. So when it is densing, there is a kind of a situation is going to happen. So in here in the figures, like you can see there's a nebula figure, like, and if you classify the plasma categories, like there is a many type of things that we know, and they are charge density. That means when they combining, like when they stay as a group, like how much of density with the temperatures is going to there, and also the classification. So the high temperature plasma and the low temperature plasma is the basic thing. Like normally in our Earth, when we do some experiments, we are dealing with the low temperature plasma, but we coming outside of our planet, like we can see the high temperature plasma. Our sun is a high temperature plasma situation. Nebulas, they are high temperature plasma situation. So when the high temperature plasma situations occurs, they provide in the things to born the stars, right? So that is what it is saying here. So when this one is giving, they try to stay in equilibrium. Okay, they, like the charged particles, when they're separating with each other, they also try to attract with each other. But due to their hot condition, they also try to stay as their groups. Normally in a nebulas, with their together, like when they're vibrating or something, like they start to stay in a equilibrium. But sometimes that equilibrium try to break it out. That is where the stars going to born. So the gravitational collapses happening in such a nebulas is going to making the stars. Like in here, like top corner of the figure, like you can see, first there will be the nebulas and some areas, the dense areas will be there, right? Then they try to attract with each other and try to collapse into a one point. When this one is happening, the energy is also getting very high. The temperature gradients, everything is going to getting high. So when the process is happening, like they have some, then after the some process, after some time, the thermal effect is going to balance with the gravitational collapse. So when that time, okay, it is going to stabilize, the star is burning. So in that time, the other parts we calling as the debris is throwing away as a disk. So when the debris also, like due to the gravitational effect of that star, that born star, when they move in, like they also try to generate some planets, the, like maybe the Jovian planets, the rocky planets, or the asteroids, they try to build that one. So the GIF also, like I'm included in here, also showing how the stars are born in here. So that is the process happening in here. Now, when coming to the classification of the stars, like we have many types, like normally we are giving the classification due to their temperatures. So considering that one, like our sun is in the G type star, right? So it is having a lifetime of 10,000 million years, right? And that one also, like when the star, our sun, also there, they are not stay in a same place, like the same type every time. Like our sun also having a cycle, right? Every 11 years, it is changing its behavior. Like in here, in this figure also, you can see the 1996, it is little bit cooler. Then it is increases temperature in the 2001, and it is decreasing again, coming into the cooler mode in the 2006, the 2007. Again, it is starting to increase. So in the 2012, it is increased its temperature again. Then again, like 2022, 2023, we are expecting the sun to increase its temperature gradients again, our sun, right? So when those things happening, like our planet also feel some tensions, like there is some experiments studies, the observational studies was conducted. So in that time also they showing that something is happening there, right? Now if we come into the like the other section, which is as the galaxy. Now the galaxy mean, like we know that the millions, billions, trillions of stars together. So sometimes with the stars there will be a number of planets, like our solar system. There will be a solar systems will be there. So when they combining together, they generate in the thing called galaxy. So due to their behavior also, we can have a different type of galaxies, right? So in these figures also you can see the basic types: elliptical, normal spiral, the Barrett spiral, and irregular galaxies. That is where we're going to classify these galaxies. So the galaxy type, like normally in the galaxy, how much of the stars going to contain in a galaxy, we are say with the luminosity or the brightness when we're considering that one, and we just giving assume numbers, because we know that there will be trillion, billion number, like, but who going to count that number, right? Are we going to count 1 to billion? Like, I think it is not possible. So we are just giving assumed values in there. Then the question is, how do we know this information? How? The answer is simple. What? From the sky observation. If we, our ancient, ancient people, like if we ourselves and our future generation, if they're not going to observe the sky, we are not going to get this information. We cannot process, we cannot analyze, and we cannot come to conclusions like this. So from the sky observations, we are getting such information. Right. Now coming to the history of the sky observation, like from 1,000 years ago, like we have in the records of the Asian people detect these things. Like, so the first evidence coming with the Babylonian era, they marking with some pillars. Then the Galileo developing the first telescope to observe the sky. So it is give more close images of the planets, the Jupiter, Saturn rings, like their behaviors, like that is give us more information. Then, like everybody know that we send another telescope, like we send satellites, kind of a satellite, the Hubble telescope, we send to the our space, and we take pictures with a high resolution using the electromagnetic spectrum, which is included the ultraviolet range, visible, and the infrared ranges. Then we get more knowledge about these objects. But if you come into here now at the moment, like everybody hearing about the newest observation equipment, which is the Webb, James Webb Space Telescope, right? Everybody hearing. So let's see what is the current situation of the Webb Space Telescope. So there will be another video I included in here. So let's watch about that one too. Can you guys see the video?
Yes, sir, it's visible.
Okay.
This is a science mission on par with Apollo missions, Space Shuttle, International Space Station, and Hubble missions. For nearly 2 decades, thousands of people around the world, many spending their entire careers, built the James Webb Space Telescope. all comes down to this.
Once we launch the James Webb Space Telescope, there are no second chances. We have 300 single-point failure items, and they all have to work right. When you're 1,000,000 miles away from the Earth, you can't send someone to fix it.
We've never put a telescope this large in space. We want to see distant parts of the universe humans have never seen before. Looking back in time, almost 14 billion years to see the first galaxies that formed after the Big Bang. And we want to search for the building blocks of life in the atmospheres of planets orbiting distant stars. To unfold the history of the universe, we must first unfold this telescope.
This is the largest primary mirror, the largest sun shield, and the most powerful space telescope ever built. And yet, this large telescope needs to fit inside a 5.4-meter diameter rocket fairing. That's the largest fairing size available on any rocket, and it's the fairing size on our ride to space. The Ariane 5, provided by the European Space Agency, is one of the world's most powerful rockets. To cheat the fairing size limit, we built Webb to fold, like origami, to fit inside the rocket fairing.
And this brings us to our most challenging part of this mission, unfolding it in space.
Six, cinq, quatre.
Think of what you're doing. You're taking this extraordinarily delicate, precise, state-of-the-art scientific instrument, you're slapping it on a rocket, and for the next 8 minutes, the explosion from that rocket is following you into outer space. Vibrating you, shaking you. Everything that goes into outer space has to live through this environment and work once it gets there without having someone come to fix it.
Weeks. That's how long it will take to fully deploy the Webb telescope. We can take longer if we need to, but those 2 weeks after launch are going to be nail-biters. This is the Mission Operations Center at the Space Telescope Science Institute in Baltimore. Those 2 weeks after launch will be like our Super Bowl, World Cup, you pick the analogy. Years of training comes down to these moments.
The Webb Observatory has 50 major deployments, 50 depending on how you categorize them, and 178 release mechanisms must work to deploy those 50 parts. Every single one of them must work. Unfolding Webb is hands down the most complicated spacecraft activity we've ever done. Then again, nothing about Webb is easy. We've never done any of this before. There's nothing simple about sending anything into space. You can't do it without taking risks.
This mission is squarely in new spacecraft territory. Webb is the perfect example of science desire driving engineering capability to new frontiers. Webb's unique design was born from reasoned engineering to accomplish its science goals.
Here's the plan. Shortly after launch, we unfold Webb's solar panel for power and our Huygens antenna for communication. About 12 hours later, we have an important engine firing that sends Webb on the proper course towards its orbital destination, about 1,000,000 miles away. That's where Webb will do its science. Webb will be moving so fast, it passes the moon's orbit in 1.5 days, half the time it took Apollo astronauts to reach lunar orbit. First, we lower the sunshield pallet, then raise Webb's primary mirror and instruments away from the sunshield. The solar wind will push us around with the sunshield open, so we'll unfold a trim tab to help keep us stable.
We got these huge, iconic, golden segmented mirrors that will help us deliver amazing new images from the cosmos. But in some ways, the sunshield is a lot more complicated, and it's just as essential. Without it, nothing works.
Here we've got 5 sunshield layers, or approximately 8,900 square feet, almost the size of 3 tennis courts, a very thin Kapton material, about 1 to 2/1000ths of an inch thick. Making them go where you want them to go in 0G is extremely challenging.
The sun shield shades the telescope from the heat of the sun, earth, and moon. The concept is simple, but there is nothing simple about the design or operation, especially when you get to space. Webb's sun shield assembly includes 140 release mechanisms, approximately 70 hinge assemblies, 8 deployment motors, bearings, springs, gears, about 400 pulleys, and 90 cables totaling 1,312 feet. All this just to keep the sun shield under control as it unfolds. First, we release these special restraints that protect the sun shield during launch. They roll out of the way, but not all the way until we are ready to deploy a side. Next, we release a set of covers over the core region. Now comes the critical point. All 107 sun shield release mechanisms need to fire on cue. 107. They free the 5 sun shield layers, allowing them to extend as the mid-booms deploy.
Sun shield fully deployed, we start setting up the optics. First, the secondary mirror is extended and locked into place, and a special radiator behind Webb is extended, which helps further lower the temperature of the science instruments. Finally, we open the primary mirror's wings and lock them in place. With that done, Webb is in its final configuration, but we're not done yet.
After 47 deployments, and accomplishing the hardest spacecraft unfolding NASA has ever done, Webb still won't be ready for science.
While the instruments cool, we'll control motors behind each of Webb's 18 mirror segments, a secondary mirror, and the fine steering mirror located inside the center of the primary mirror. We'll precisely align the mirror segments to form a perfect mirror. Then, Webb will be ready to explore the cosmos.
Right. I hope now you have an idea about the Webb, James Webb Space Telescope situation. Like in here also, like if you watch the video, you can see many physics was used, like theoretically and practically also used. Right now, now we are coming to the closer to the second part of the session, right? Which is even though we do the sky observation using, like we came from the normal naked eye observation with the general telescope, then the Hubble telescope to the James Webb telescope, but these things are not effective. Why? Because these things using the electromagnetic waves, we know the EM waves, ultraviolet, visible, X-ray, infrared rays. But when they're traveling through the objects, like through the black hole, they're not coming out. So how are we going to get the information about the black holes or the neutron stars? If they're having a binary system, like combining with the black hole, neutron star, or the black hole with the binary star, how are we going to get information about those things? So that is where we are failing. So to overcome this matter, like the scientists, right, come into the new area, right? That is the gravitational wave. Identify, detect this information, and get the information regarding the born of our universe, right? So with that one, we can get the information about the black holes, the neutron stars, the things we cannot earlier detect, right? So for the gravitational wave astronomy, normally we are telling any object having a quadrupole moment can form a gravitational wave. But what is mean by quadrupole moment, right? So I will explain about what is the quadrupole moment in here. Like the normally moment, like we know that one, like where So like then if for the monopole, like now we are dealing with the mass structures, because the gravity is generated by the object with the mass, right? So if it is only the total amount of the mass value, then we are saying monopole. That means only a single dimension we're going to discuss. But if we have the distribution of the mass along an axis, then we are saying it as a dipole. Now the quadrupole mean now we're going to have the two types of these quadrupoles, and they moving with each other. So the total effect is not in a stationary place, like they're going to vibrate, right? So when such a thing is happening, we are saying the polarization, or sometimes we calling as a tensor, that when it's happening, we are saying the quadrupole moment is generating. Actually, when we come into ourselves also, like we also have in that one, but it is very low to detect. So that's why at the moment we are only focusing to the objects which is having the higher mass values, like the black holes, the neutron stars, the binary star systems, like with which they are going to have a high mass values. So with that one, we can detect these gravitational waves, right? So that is why we focus into those things. But actually, when we come into our bodies also, we also generating such an effect. So when we come into the astronomy, like these things, like this quadrupole moment, like we are saying as a polarization, we have a two type of polarization. One is a plus polarization, and the other one is a cross polarization. So when it's expanding around, like it is coming to a prostate position and the obsolete position, like we are saying as the plus polarization. But when it is having a kind of the phase polarization, we are saying that is as a cross polarization. Right, now let's come into the astronomical sources. Like I also tell about that one earlier, like every objecting having this quadrupole moment, like when we're moving with another person, if you're going to talk with another person, like when we are in the child time, like when we're playing with another person also, we also generating such a waves, the gravitational waves, but they're very, very low. It is very so difficult to detect. But when we considering the very large objects, like merging of a binary black hole merger, right? Binary neutron star merger, or the black hole neutron star merger, we can observe these things. And the supernova core collapse also, we can observe these things. So in these figures also, you can see like such information when it's when they're merging, like they doing kind of a disturbance in the time and space. So that is where the gravitational waves are generating, right? So in here, this Jeff, it is showing kind of what is how the happening, like merging of the two binary stars, right? So when this one is happening, okay, it is making the ripples, like throughout the space, right? And like this figure is you can see it is like a kind of a 2D wave transmission, but actually when we come into the space, it is a 3D ripple situation is happening. Right, now for the evidence, like for the gravitational waves we are observing around in the 1974, but this concept was postulated by the Einstein in the 1960s. We all laugh to that person. Like if I was in that time period also, I'm also going to laugh in that person. How are you think everything is a wave? Like, but he postulates something, but with the later development of the technologies and with the knowledge development of the knowledge also, like we like with some experimental evidences see that this postulate is correct, right? Now we need some technique, right? So the Einstein postulate that one and some observation showing that okay, that postulate is correct. Now we need to conduct some experiment to confirm this postulate. So that is how it is going to become a theory. So now for detection strategy for this experiment, at the moment we are classifying into 3 generations, right? So the first generation, like they use the cylinder, like Weber cylinder, we are saying as an antenna, right? So with that concept, like the plus polarization kind of a concept we use in here, right? When we use in that one, we have a cylinder with the detectors. We are expect like with the cylinder with these gravitational waves, it is going to expand and like it is going to change its behavior from postulate to obsolete condition and come into the again spherical condition kind of a situation. We detect that information, but when we calculating these values, we are getting a very like the loss of the mass value of such a system is 1,000 solar mass per year. It is a very large value. It cannot be happen. So that is where we want to develop a new method using the interferometer technique. I hope you everybody heard about this one, Michelson interferometer. Like, so such a system we're going to use in here, right? So the second generation, like we developing the interferometer technique. So Michelson interferometer technique we are going to use, but we going with a larger arms, right? So when the interference is happening, like through that one, we can generate the interference pattern, destructive interference or the constructive interference pattern. So with that one, we can observe the gravitational wave behavior. So like next slide, like you're going to get an idea. Now, normally we're going to do is like in here, using this system, we're going to emit a laser. Then there will be a 2 mirrors, like in the Michelson interferometer also, we're going to have a 2 mirrors. But in the like normally in our experiments, we have the manual control about that one. But in this system, the gravitational waves is going to change the position of these 2 mirrors. So with that one, we're going to get the interference pattern. So let's see about that one. So then now the one part is reflected, one part of the wave is transmitted. Now they again from the 100% reflective media mirrors, okay, they coming back again. Now they again going to interfere at some photo detector, but with the position, with the gravitational wave positions, like what we can observe is like we can observe a kind of a interference pattern. One is a constructive and a destructive interference we can observe. So with that one, we can estimate what will be the wavelength of these interference, right? So that is what we're going to use in here in this concept. Like, so this kind of a setup is built in the 5 places at the moment in the world. One is the Hanford in the USA. The one is the Livingstone. Now this gravitational wave detection is like this concept came into the like the scientists tried for many years, but this came into the public domain when the Hanford and the Livingstone, they both simultaneously observe this incident. They pick a individual incident and they simultaneously do the measurement, and it is came to coincide with that one. That is where we first confirm the like more accurate gravitational waves. But there is another facility in Italy, Virgo, and Geo 600 in the Hispania. Then in the Japan also we have it. So one of our colleague who's work in the Sabaragama University also, he studying about this gravitational wave, like, so he having some connection with the Kagra, Japan. Then let's come to detect the gravitational waves. Now we have in the equation, we are going to relate that one with the relativity concept because it is came with the Einstein concept. So with the Michelson interferometer, when the Earth is getting the gravitational wave impact, like, so the mirrors also going to change. So it is giving the interference pattern. So with that one, we are saying the stretch, right, or the strain, we're going to get as a delta L. Right? When we get in that one, it is a the simple H value in here, like the space dimension changing factor, like, or the strain, right? Normally, when we calculating, it is into the 10 to the power minus 21 meters. That means, like, we know that the inside the atom also in the 10 to the minus 15 scale. So that means these strains are very, very small. Then if we have the increase of the length, that means, like, if we can increase the beam of these mirrors, like the interference beams, then we can get the delta L difference. Like with that one, we can more confirm that one, right? So that is what we observe up to now. Like, so here we have in the like in the below three figures showing the interference patterns, like with the strain values we simulated, the calculated using the observed interference patterns. Now in the middle picture, yeah, you can see the H1 and the L1, like the first incident of the gravitational wave, which is detected by the both these observation centers simultaneously, right? So the red color is the spectrum for the Hanford observation, and the blue color is for the Livingston observation. So both are mostly coincide with each other, which is gave the correct or the thumbs up to the gravitational wave existence. Now, when we observe in the gravitational waves, we have a kind of a notation, like we are saying GW, and we're going to have a kind of a number when we have an observation. Like, so the first two numbers belong to the year, the second two digits belong to the month, and the third two digits belong to the date. So that is how we're going to detect or the name the gravitational waves. Then when we come into the another notation we are getting, like how many observations we're going to get, how we're going to classify that one, right? So in here you can see the markings in here. O is representing the observation of the gravitational wave, and simple N is the what is the number, and X is the what is the phase. Like, rather than listening to this one, like, let's move to the next slide. Like, we're going to have a clear image about that one. Now O1, that means observation 1, the number will be 1. So in that time period, right? So 2000 September 2015 to January 2016, the scientists able to detect 3 events. But from the November 2016 to January 2017, it is the observation number 2nd. So in that time 8, and in the April 2019 to September 2019, like they observe some situation, like the number of events, the 44 events. But in the 2019, they started another observation phase going to the 2020. So that's why, to combine in that one, they dividing into 2 phases, A and B. Like, so with that one, it is going to continue with the for the 2021 situations, like it will coming with the observation 4 and go on. Like, here is another kind of a simulation. Like in the below, you can see when we simulated what we observe when we get in that information from the interference, like we simulated that waveform, like, and when we plot for the simulation how these two binary system coming together, how the space-time disturbance is going to happen. Like, so that these arrows pointed in here, it is they making the things as the vectors for the mass or the gravitational vector they showing in here. Right now, this is like a kind of a periodic table, like when we have in the detections or something, like up to now, like not up to now, like up to the 2020, like they classify that one into a kind of a notification system. Now in here, like if you take a one, like so here the first three belong to the O1. Like the previous slide, I told that the first observation, like we have 3 events detected. Then O2 phase, 8 events. Then O3 phase, like we have another 38 and 44, those kind of detections that was listed in here. And if you take a single one, like you can see there will be a 2 smaller dots, and in the middle there's another big dot. Now these smaller dots mean the binary system. Like so each binary system, they're going to have their own mass. Like so the number representing in there belong to how many solar masses. Like so if we come into the first one, like the smaller 2 smaller dots equivalent to 36 and the 31. So the primary mass and the secondary mass values, like the primary mass is 36 times than our solar mass, and the secondary mass is 31 times than our solar mass. When they have merged together, they generate another one, like so the final mass is become 63 of our solar mass value. So that kind of a simplified information is going to help to the scientific community to have an idea about what kind of a information we collected to identify the gravitational waves. Now at the moment we are in the generation 2. Now we are coming to the generation 3, like the future in the gravitational wave astronomy, right? So we want to, like with this technique we can detect up to the astronomical objects up to the 1 billion years after the Big Bang, right? And we normally are doing that because with the time period the frequency is going to reduce. So 10 to the 1000 hertz scale, we are doing that one, right? So these interferometers, like we use with the BBH, BNS, that means the binary and the black hole and the binary and the neutron star mergings. Like so, and the arm length of the interferometer technique, we using about the 4 kilometers. But if you remember, like previously with that equation, the delta L depend with the strain multiply with the length of the interferometer. So if we can increase the interferometer length, that means we can increase the detection length also, right? So in the next generation, we are saying as the third generation, we are expecting to get the astronomical objects or the information about 0.1 billion years after the Big Bang. That means the million years, 100 million years after the Big Bang. So normally we are saying in the astronomic scale, like we are saying it is as a dark age. And we have at the moment the concept, like we're going to launch in the near future Einstein Telescope, the Cosmic Explorer, and Laser Interferometer Space Antenna, which is in a simplified, we are saying as the LISA. What a beautiful name to give to a girl. Like if you heard the name of a girl having a Lisa, you can say, oh, you are the Laser Interferometer Space Antenna. She's going to be confused. So like we can use, we're going to use these new 3 interferometer techniques to detect the gravitational waves. Then with the time, these generation also going to improve, and we're going to get more and more accurate detection strategies to get more information about that one. So if we come into the Einstein Telescope, like it is expecting to increase its length, the arm length, to 10 kilometers. Like in the Italy, the Virgo, right? That institute, normally they have in the optical length of the 3 kilometers, but they expecting to expand that one to the 10 kilometer under the Einstein Telescope. And to have a more accurate pictures, the thermal noise, we need to remove that one in the photo detector. So we also try to cool that one, the components, to 20 Kelvin scale. So we can reduce the heat effect and get more accurate readings on the the gravitational waves, right? So with that one, with this telescope, we are expecting to get the information about the near black hole horizon, right? So and the nature of the dark matter and the dark energy, right? Because like we also know that the dark energy, dark matter is containing so much of the universe. So if they containing, that means they're also making the gravitational waves. So we are expecting to get more information about these things. Now let's come into the cosmic explorer. Like in here, we also expecting to expand, like in the US start this project, like they expecting to have the interferometers with the optical length of 40 kilometer and the 20 kilometer arm length, right? So with that one, they expecting to detect the merging of the first black holes in the universe. Like when the galaxy is forming, in the center, they're going to have kind of a black holes, the very big ones, the massive ones. So detect those informations is expected through this cosmic telescope, right? So with that one, now here is listed a few of the things which is going to get through the cosmic explorer telescope. Both these telescope types, even though it is having the telescope, it is going to build in our planet, right? In the surface, right? But the LISA, we're going to build in the outer space, right? So we expecting to launch 3 spacecraft, which is going to place in a triangle. Like in the animation also you can see the 3 satellites, like they moving with our Earth, which is showing in the blue color, right? And each like for that triangle, right, equilateral triangle, each slide going to have a 2.5 million kilometers. So that means the L value is so much increases. So with that one, we can detect more accurate gravitational waves passing through our Earth. So with that one, frequencies of the 0.1 millihertz to 1 hertz range gravitational waves we are expecting to detect, because we are increasing the L value. So with that one, we are expecting we're going to get more information about the formation about our universe. So that's all about the gravitational waves and the astrophysics part. And I hope you have an idea about what about the astrophysics and how the gravitational wave is come up to now. So thank you very much for your attention.
Thank you very much. Today's guest speaker, Mr. Thomas Leon, Dr. Thomas Leon Suganda Fernando, for dedicating your valuable time for us. I believe that was really an informative and effective session. So on behalf of all the participants, I really appreciate this precious session, and I'm very much grateful for all participants for their attendance today.